Welcome to The Explainer. Today, we're going to talk about something pretty radical. What if the biggest, most complicated problems you could throw at a computer could be solved instantly? Yeah, instantly. We're diving into what's being called the post-algorithm era, a change that isn't just about making computers faster, but about fundamentally changing what it means to compute at all. And this line right here, it just perfectly nails it. We are not talking about a slightly better chip or some clever coding trick that shaves off a few seconds. We're talking about a completely different category of problem solving, a world where, for some really hard problems, you might not need a step-by-step algorithm anymore. Let's see how that's even possible.
All right, so here's the plan. First, we're going to tackle this wild claim about the end of algorithms. Then, we'll look under the hood at something called the Atlas structure, which is the engine that supposedly makes all this work. We'll trace its roots back to some incredibly deep, beautiful math, stuff that was discovered, not invented. Then we'll see how a system called Hologram brings that math to life as actual code. And finally, we'll just try to imagine what a world with this kind of technology could look like.
So, what does it really mean to be post-algorithm? Well, it all starts with throwing out one of the most basic rules we've always followed in computing, the idea that bigger, harder problems have to take more time to solve. This slide really lays it all out. On the left, that's the world we live in now. It's like a tortoise. The bigger the problem, the more data you have, the longer the journey takes. Computer scientists call this polynomial time, or O of n squared. But on the right, that's the rocket. It doesn't matter if the destination is a mile away or a million miles away, it gets there in the exact same amount of time. That's O of 1, constant time. The travel time is fixed, no matter how far you're going.
So, if the size of the problem doesn't determine the speed, what does? Well, it's this number, 194. That's it. That's the new speed limit, and it's a constant that comes from a really deep property of mathematics itself. We'll get into where this number comes from in a bit, but for now, just remember, it never, ever changes.
Okay, I know what you're probably thinking. This whole constant time thing, it sounds a little bit like magic, right? So how does it actually work? Well, the secret is this new kind of computational framework called Atlas, and it's built on 4 key ideas, or pillars.
First pillar, the character table. Okay, think of it like this. Instead of using a calculator to multiply 2 huge numbers every single time, what if you just had a giant cheat sheet with all the answers already written down? That's basically what this table is for matrix multiplication. It's a 194 by 194 grid of pre-solved answers. The calculation is just looking up the right row and column, and that's always an instant O1 operation.
Second, we've got orbit classifications. This thing acts like a perfect sorting hat for your data. It automatically splits any problem into exactly 32 completely independent channels. So imagine you're trying to find the tallest person in a massive stadium. Instead of one person running around with a measuring tape, you split the crowd into 32 sections, find the tallest person in each section at the same time, and then just compare those 32 winners. It's perfectly parallel with zero coordination needed between the sections. Then there are unit groups. This is cool. It basically does for division what that character table did for multiplication. Division for a computer is usually a pretty messy, repetitive process. But this structure turns that slow calculation into another simple lookup. You just find a number's inverse and multiply. Boom, another instant O1 operation. And the final piece of the puzzle, resonance operators. You can think of these as 96 parallel referees, all watching the game at the same time. While the main calculation is happening, these 96 channels are constantly double-checking the work, tracking the precision of the numbers, and verifying that the final answer is correct. So it's not just insanely fast, it's provably correct, with the proof built right into the computation itself. Okay, so this is the part that is just mind-bending. Where do these seemingly magic numbers, 194, 32, 96, where do they even come from? Well, they weren't picked by an engineer trying to optimize a system. They were discovered, like finding a new law of physics that was there all along.
And it all starts with this number, 196,884. It looks totally random, right? But it's not. It is the dimension of a mathematical space called degrees algebra, and it turns out to be the hidden key that unlocks this entire structure.
So you have to ask, right, why that specific, enormous number? What's so special about it?
The answer is just wild. It goes back to a famous mathematical discovery in 1978 called monstrous moonshine. A mathematician noticed that a key number from one field of math, 196,884, popped up in a totally unrelated field that studies the symmetries of a bizarre object called the monster group. Now, you don't need to be a math whiz here, but the takeaway is this. This was a clue that pointed to a deep hidden connection in the fabric of mathematics, and it's that fundamental structure that this Atlas system is tapping into.
Okay, so we've got this beautiful, deep, almost mystical math. But how on earth do you turn that into code? You know, something a computer can actually run. Well, that's where a system called Hologram comes into play.
Hologram basically flips the whole idea of programming on its head. Usually, a compiler tries to make your code run faster when you execute it. Hologram gets rid of the running part completely. At compile time, it uses that Atlas structure to solve the problem for every possible input, and then it just saves all the answers in a tidy little lookup file. So when you run the program, it does zero work. It just looks up the right answer, which is already sitting there waiting for you.
And this is the kicker. The payoff for doing all that work up front is a tiny file. We're talking around 36 kilobytes. Think about that for a second. You do the hard work one time, up front, and in exchange you get a file that can perform an incredibly complex operation instantly, forever.
And what's really amazing is that because this whole thing is built on pure math, the system doesn't care what problem you're solving. That little 36 kilobyte file, it could be a layer in a neural network, a gate in a quantum computer, or a filter for an audio signal. The underlying mathematical language is universal.
So, let's bring it all together. We have a way to get instant, provably correct answers based on the deep structure of the universe itself. What does that actually mean for us in the real world? What happens when the biggest bottleneck in modern technology just disappears?
Well, for something like AI, the change would be staggering. Running a query on a huge language model, a task that takes seconds or even minutes on the best hardware today, could take just 35 microseconds. To put that in perspective, it takes you about 300,000 microseconds just to blink your eye. And that 35 microsecond number, it's not an estimate, it's a mathematical guarantee.
This opens the door to things that have always felt like science fiction. In AI, you can have a real conversation with zero lag. Perfect simulations of how a new drug will interact with a protein, with no approximations. And maybe the biggest deal of all, AI systems for things like self-driving cars or medical diagnoses that aren't just reliable, but are mathematically proven to be safe and correct.
And that really leaves us with this one final, huge question. For pretty much all of modern history, our ambition has been limited by how fast we can compute. If that limit just goes away, what's left? The only bottleneck is our own imagination. So, what grand challenges will we decide to take on next?